Let's discuss the basics of the Hom and Ext functor in the BGG Category O. So the homomorphisms in the Category O, for instance, from a simple module with highest weight lambda to another simple module with highest weight mu, is just 1 when lambda is mu, and otherwise it's 0. So that's the dimension. This is a sort of generalization of Schur's lemma. Next, we observe that Hom is actually a left exact functor, meaning it maps short exact sequences into long exact sequences, which are zeros starting from the left. This is what it means to be left exact. Moreover, in the second argument, so for second argument fixed, it is contravariant, which means that if we have a short exact sequence that goes from A to B to C to start with, then Hom in the second argument will reverse the order in the first argument. So for instance, Hom CD, so it's left exact, and we'll have Hom CD going to Hom BD going to Hom AD, and then it goes on. And the way it goes on is it goes into the first Ext group by definition, and it continues in the same order. And then if it goes beyond that, which we will not do here, we'll go to the second Ext group of CD, etc. Now, one way to think of the first Ext group is to think of it as a measure for the non-trivial extensions of A and C by B. So if this is a split exact sequence, then B is A plus C, and we call this a trivial element of the Ext group, but there may be non-trivial extensions. Now it's important that we look at the Ext group inside O, and sometimes denote this by Ext in O. That is to say, we only look at extensions of A and C which are inside the category O. The importance of this is clear from the following example. If we build a representation with a highest weight state on which H of SL2C, we take the example of the semisimple Lie group SL2C, we take H the Cartan generator, we have it act by lambda 1 lambda on two highest weight states, then actually this generates a highest weight representation in which we can embed the Verma module M lambda. So M is the highest weight representation with these two highest weight states, and M lambda is embedded both, well, we have the short exact sequence like this, where M lambda is inside M, but in fact, M clearly is not equal to M lambda plus M lambda. Therefore, the sequence is not split. However, note that this example, M is not inside the category O because the representation does not split into eigenspaces of the generator A. So it's not a sum of weight spaces. And so this is not a valid extension inside O. All right, so what can we say about these extensions existing or not? It should be clear that this gives us some handle on the structure of more or complicated objects inside the category, like how complicated can they be, which complications can arise. So let's enumerate properties of Hom and Ext. Firstly, if M is a module, a highest weight module of highest weight mu, where mu is different from lambda, then if one has an extension like this by m lambda, then this will automatically split because E lambda inside E, which is the pre-image of the highest weight vector of m lambda, will automatically generate an m lambda module inside E, which is isomorphic to the last one, and this will split the sequence. So therefore, Ext of m lambda in M is 0. Now, similarly, one has that there are no non-trivial extensions of m lambda by m lambda. So in other words, it's always a direct sum. And also there are no non-trivial extensions of m lambda by l lambda. Now let's look at the less trivial case. Let's suppose that n lambda is the maximal submodule, as usual, of the Fermat module m lambda. And let's suppose that lambda is different from mu. And one can prove that the group of homomorphisms from n lambda into L mu is equal to the extensions of the simple module L lambda into L mu. This is a simple consequence of homological algebra. So one starts with the short exact sequence n lambda embedded in m lambda. The quotient is equal to L lambda. This is the short exact sequence. And this gives rise to, because of left exactness of Hom in the second and contravariance in the second argument, this gives rise to, amongst others, this terms in the sequence. So we have m lambda L mu, and then we have to go to the left. So Hom n lambda L mu. Very good. And then we get to Ext of the last term. So that would be L lambda L mu. And then we get to Ext of L lambda m lambda, and so on. And then we've already proved that this Ext group is 0. And we have proved that for lambda different from mu, these homomorphisms are also 0. And therefore, we conclude that these two terms in the sequence are equal, which is exactly what we needed to prove. And lastly, very similarly, one can prove that there are no non-trivial extensions for a given simple module. So these are a few properties, a few simple properties of the extensions and homomorphisms of the elementary elements of the BGG Category O.